All right, good morning. Welcome to Friday. Yeah, it was a long time coming for some reason, but we made it to Friday. That's good. All right, so this is the end of week 9. And I'm really hoping that everybody has finished homework 8 and submitted it and is all good to go with that. And I know that's not the case because I tried downloading and fewer than half of the people in this course have actually submitted homework 8. So my suggestion a week and a half ago when we started this was, pretend that it's due today at 8 a.m. and make that your deadline. And if you make that deadline, then, you're done with homework 8, you're done with programming assignments for the course, and you've got the weekend to work on other stuff. And if for some reason Friday morning at 8 comes and you don't have this completely working perfectly, you can ask questions in class, and if that doesn't work, you can still catch me in office hours at 2. So those are kind of the stop gaps. So if people were taking that advice, that means that, 30 some people are in some kind of dire straits right now and are having some kind of problem they can't solve. So I really want to talk about this. I really want to get through these problems now and or in office hours at 2, and that's it. There's going to be no help over the weekend. All right, so this is your time to ask those final questions. You got leading spaces in your thing you can't input from standard in. Whatever the issue is, let's go through it. All right, I think I'm done, but I have one question. When using user input instead of providing a file, the only way I found to get out of the read loop is to press Control-D. That's exactly the right thing to do. So when you read from standard in, if you are at the beginning of an input line and you hit Control-D, that is interpreted as end of file. And that's exactly the same situation as if you're reading from a file, if you're redirecting standard in, and then you try to read past the last line of the file. Or if you're reading from the output of a command through a pipe, and then that command closes the pipe, typically by exiting. Those are exactly the same situation as hitting Control-D as the first character of a line. So yeah, it's exactly the right way to signal end of file when you're testing this. Alright, I have everything done except can you go over that regex that you used with sed to remove leading spaces? Sure. So let's do some sed. And let me do this interactively. And I'll even throw some leading spaces at the end. Alright, so if I echo $line, I don't know if it actually ingested those or not. Interesting. Good question. All right. So there's our line that we've presumably read from a file. We've interpreted it as a phrase. It would be uppercase and so on and so forth. So first thing first, though, right? If you're doing debugs, right? If you echo your phrase and you don't have it in quotation marks, you're going to lose those leading quotes, even though they're there. If you put it in quotation marks, you can see those leading spaces, but you don't have any idea if there's spaces at the end. So this is why, I like to put delimiters around variables that you output because it makes it really clear, hey, there's a bunch of spaces at the end here. And if you don't know those are there and you're using them as part of your phrase, you may end up not associating phrases. All right, so there's our phrase. Let's go ahead and remove the leading quotes. So this said string will look for a pattern beginning at the start of the line, followed by any collection of spaces, and if it finds that pattern, it'll replace it with nothing. So if I just type something in here, right, it removes the leading spaces. So if I want to do this from a variable, I can say echo quote $line, and I can pipe that into this same sed, and then instead of sed reading standard in from the keyboard, it will read it from the output of this echo, which should be this big long string, right? And so that shows me my cleaned up line. And then if I want to use that in my script, here's a suggestion: make a new variable. Let me call it line 2 and set it equal to the result of this sed's output. And let's output the value of line 2, and you can see the leading spaces got removed. If you want to get rid of trailing spaces, let me put that into line 3. In trailing spaces, I'm going to look for a succession of spaces. That's what the space with an asterisk means, followed by a $sign. $sign means that's got to end at the end of the string. And then if I output the value of line 3, now it's all cleaned up. No spaces in the beginning or end. And so yeah, if you wanted to get rid of leading underscores, you could do that. All right, let's see. It's due Monday. I thought half the class didn't do it and it was due today. Yeah, that would be bad. Yeah, leading underscore is exactly the same thing. So the only problem I have is that after the period mark, some phrases can start with an underscore. Is there an easy way to read like the first underscore in the phrase and remove it? Yep, so this will all work with underscores. Alright, so there's our line, and if we say line 2 equals this stuff, then line 2 is the cleaned up version. Alright, how do you deal with a new line that doesn't have the end of a phrase on it? For example, if you typed hello, comma, bye, new line, bye, my program will take that as hello and 1, bye, bye. If the bye ends with a new line and you're reading one line at a time, so you type hello, comma, bye, and then you hit the enter key, and then you type bye again. So this should be two phrases: hello, which occurs once; bye, which occurs twice. And there's nothing to take care of with that, right? If you're reading your input one line at a time, the first time that you say, read from standard in, this is what you're going to read. You're going to convert it to uppercase. You're going to compress your spaces. You're going to change your comma into a single space, and this is going to look like hello space bye. And then when you say for P in, phrases, you'll loop through that inner loop twice. The first time your variable will be hello, and you'll load that into your array. The second time your variable will be bye, and you'll load that into your array. So hello will be a 1, and bye will be a 1. And then when you're done with that inner for loop, you go back to your outer while loop, and you read another line, and this is what you read. right? And there's a new line at the end. And you uppercase it, you change things around and so on and so forth, and this is going to leave you with a phrase, by. And then when you go through your inner for loop, it's going to set p equal to by. You're going to look in your array, see it been in there once, increment that, bump that to a 2, and now your associative array says I saw hello once, I saw by twice. So you'd have to work really hard to turn by into a phrase. You'd need to be reading in multiple lines and joining them together, which is not what you want to do. And I thought that was a regular expression there. I was like, wow, I never realized the shruggy symbol was a regex, but it probably is. It would be interesting to throw that through SID. Yeah, so if you do something like you know, variable equals /dev/standard in, right, or, you know, cat/dev/standard in, then it'll pull in like all of your input and throw it into one big huge line, right? And you don't want to do that, because that's going to blow up if you feed it a limitless amount of input. If you process it line by line, there's theoretically no limit to how much input you can feed to your script, and it'll just keep, you know, taking it and tallying it, and there's no growing resource consumption. All right, what else? Oh, that would have been an awesome Easter egg, man. What is the exact output supposed to look like again? Exactly like this. So number of appearances of the phrase, a single space, and then your phrase in uppercase with, you know, spaces instead of underscores, and so on and so forth. And for the big E, right, you can see the number is left justified and so on. Now, the output from your program may not be in the same order as these. Right, because there's no requirement that you sort the output by number of occurrences. But if you take the output from your script and run it through sort-n, it should be exactly like this. And I'm just going to run your program on the input script, put it through sort-n, compare it character for character with this, and it should match exactly. If there's any deviation from it, right, that'll cost points. And yeah, you can check it yourself. So there's these output files in here. And right, so I can generate my output file for test case 2 and compare that directly using diff with test2.out. And if there's no output generated, then it matched perfectly. if there's any differences, wow, the machine's really slow. Or CMP, I've never used CMP, but I think it's the same thing. Right, so if there's any differences, like you have a leading space in there, then when you run the diff command, you'll see something saying this was a line from the first file, this was a line from the second file. Less than means it appeared in the first file and not in the second, and this appeared in the second but not in the first. Must be my network. My network died a little while ago. Alright, what else can I help you with? Okay, well, if you're not done, try to finish by 2 so you can catch me in office hours. The test files, how do we use them? The way we just did. So I tried to do that and permission was denied. What exactly did you try to do that said permission denied? Because this should definitely not be giving you a permission denied. Were you in your home directory or were you sitting in /temp maybe? So try it with just this part without redirecting the output. Yeah, try it with just this part of it, right? Pipe it out to sort-n, and if that's giving you a permission denied, double check because there might be a typo somewhere. If this is working but redirecting to an output file is giving you a permission denied, check what directory you're in because you're probably in a directory you don't have write permission to. And that's where you can do things. That's where you can do things like, show me what directory you're in, and then, type in your command and get that error, and then copy all of this, paste it into an email, send it to me. All right? Or, come by office hours and screen share. So someone said there's a 0-byte file at etc homework A test 0. All right, so this is not the file you want to use. Right, that's kind of a bogus test file. It's got nothing in it. But you want to look at the files inside homework 008 tests. Yeah, run main from your home directory, or run it from, the directory that you're developing in, your homework 8 directory, but your own homework 8 directory, as opposed to a different one. Let's say I'm logged in as my test user. right? If I try to write into a file in this directory, I'm going to get a permission denied, right? But that's because I'm sitting in a directory that I don't own. So that would be the most likely case. But yeah, you can run it from your home directory, or your home directory / homework 8, or whatever directory it is you're working in. All right, good. Other questions? Yeah, you can run it from any location. You just can't redirect the output into a directory you don't have write access to. So for sed, instead of leading spaces, how do you remove all spaces? So there's our line. If you say substitute a space with nothing, and then you put this /G at the end, that says do it everywhere in the line. So if I echo $line and I pipe that into that sed, that'll remove all the spaces leading, middle, and end. And it'll consume multiple spaces the same. Cool. All right, what else? If you get no output from diff, then the files were the same. But eyeball them just to make absolutely sure that they look, reasonable. Because it's possible that no output is not totally satisfying. So eyeball the file, make sure it has stuff in it that looks close. And then, if diff is not giving you any output, the files match. But if something goofy happens, like you're not producing any output at all and you're comparing it to an empty file somehow, then diff won't give you any output either. So that's why I say just kind of eyeball the output yourself and make sure it looks plausible. And diff is a cool command. It does a lot of stuff. Including giving you instructions to turn one file into another using a command called patch. And the stuff that it sends you out is meaningful. Gives you a measure of the differences. So the assess command uses diff to basically match your output to the desired output. And I used to crunch that and give you a numeric grade between 0 and 10 based on how different your file was. But that ended up working against people, so I changed it to just binary grading. But diff is useful to know. Oh yeah, so there was a previous Git question too. Do our Git repos need to only have main in them? No, so I'm not putting any kind of strict requirements on your Git repo contents. I think it's good practice to always put a README in there, but all I'm going to do is download your repos Monday morning at 8. And then I'm just going to use your main program, and I'll run it against my own my own suite of tests. So all I've got to have is an executable script called main. Make sure it's executable. Make sure it's called main. All right, I know we went over this a couple of minutes ago. Testing files didn't work. Can you show me the line of code to test your main with your tests? And what I see on my end to tell if it works? Sure. Let's see. I'll tag this one. So let's say I want to run, I've got my main program and I can type some stuff in. And I hit a Control D at the end and it shows me my output. Well, I type ASD a lot, I guess. Alright, so there's my output. So I want to run it against the canned tests. So type in the name of your script, less than, this is on the Linux server, /temp/homework_a_test/ and let's go against test0.in. Okay. If you run this much, you can look at the results and it should look, plausible. It shouldn't throw up or crash or things like that. So if you want to compare this to the captured output, take this, run it through sort-n. That shows you your output in increasing frequency of phrases. And save that output into a file. I'm just going to call it myout.0. Right? And then to compare that to what the output is expected to be, you can say difference myoutput.0 and compare it to temp homework008 tests / test0.out. Test0.out. And as long as it doesn't generate any output, those files match perfectly. So you can do that for all 5 tests, test 0 through test 4. I don't know why I'm getting so much lag talking to the server. I don't know if anybody else is seeing that or not. Alright, so that's basically your line. Processing test 4 doesn't take a lot of CPU time. It's mostly seems to be I/O bound and probably other stuff. And the load average on the machine is minuscule. It's 0.02. I mean, you can't get much lower than that. It's Friday, lagging as expected. Maybe. We're the only ones using this machine, so whatever habits we have as a class, I guess. All right, other questions? Cool. If you think of stuff, go ahead and pop it on there, or come by office hours 2 o'clock. My test 0 works fine except for the last phrase. It reads it twice instead of 3 times. So yeah, check the spacing. If there's a leading space in the beginning in your output, then you've got to do something more to remove spaces, leading and trailing. All right, so Yeah, that's a good suggestion. Leave the underscores in place when you output at the end. That can make it easier to see if there's extra stuff in there. And you know, you're trying to not have to deal with spaces internally, so that's why I suggest, you know, at the end of that cleanup section, change all your spaces into underscores so that the phrase you're using to, you know, search the array, to load something into the array, is just a bunch of non-space characters, right? And that's usually pretty easy to work with. So you can leave it in that form when you output. That's a good suggestion. All right, so let's talk about the fork call. So we're back to C. We're talking about some system programming concepts related to processes and process construction and management. So the most interesting, well, one of the most interesting functions we're going to talk about is fork. Okay, fork is a manual section 2 function, which means it's pretty low level, right? So chapter 3 of the manual are things like, you know, printf and fgets and stuff that you would use kind of as a typical user. The chapter 2 section of the manual contains the lower level stuff. So fork, for example, for creating a process. Read for doing low level binary input from a stream. And things like that. So we're going to work a lot with chapter 2 functions for the next few subjects. So fork is a really interesting call. Fork is used to create a new process. Every process that you have running on the system is the result of a call to fork. And how are we going to specify a process that we want to create? I mean, when you start a new process, you have to know who owns it, and what is this process doing, and how much memory is allocated for it, and there's a whole lot of information you would have to specify. And you could define a function that lets you specify, you know, a zillion arguments saying, you know, run this program and make it owned by this person, and you know, here's the priority for the scheduling, and so on and so forth. Fork is the exact opposite of all of that. It runs with no arguments at all. So what does fork do? This basically clones the current process. So when you call fork, you create a new process which is an exact copy of your current process. It's almost exact. If it was an absolute exact copy, you'd have problems because, you know, the clone and the original would both think that they were the original. And you've got, you know, the classic sci-fi problem. So what do you do when you make an almost perfect clone of someone in the movies? You throw in some little marker, right? In one, it was a little mark on the inside of the eyelid. There were little dots that would show, you know, what generation clone you were, so that someone could always tell, was this the original or was this the copy? So fork does the same thing. It makes one difference in the cloned process. Or it kills you and takes over your life. Yeah, that's always a good option. So fork takes no arguments, and it returns what effectively is an int. It's a PID underscore T, which is basically an integer. And the difference between the original process and the clone is this return value. So if you're the original, who's also called the parent, fork returns the process ID of the clone, which is called the child. So if you're the parent and you make a call to fork, if you look at the value returned by that call, it will be an integer, which is the process ID of the newly created process. But if you're the copy, if you're the child, fork returns 0. And this is fun to think about and to work with and to write code for. Because as soon as you call fork, you have two copies of your process running, and they're running the same program, and they're at the same point in the program, which means they're both at the place where they just came back from this call to fork. And if you want these two programs to do something different, it's up to you as the programmer to cause some differentiation in behavior. And the way we kickstart that differentiation is through the return process. The return value from fork. All right, so we need some stuff for fork. So let's write some code. Alright, so we will print out a message in the beginning saying I'm a process. And we'll print another message saying we're ready to call the fork command. And then we're going to say, you know, fork return equals the return value from fork. And now we're going to print a message back from the call to fork. And let's print out what the value of this variable is. All right, so that's it. A couple of prints, a call to fork, a couple of prints. All right, so what do we got here? We ran F1. It said, hello, I'm a process ready to call fork. And then it said back from the call to fork, and the return value is 28,996. And then it printed some more stuff, said back from call to fork, the return value was 0. So these two lines of output presumably came from the clone. All right, so let's do something. Let's put a call to sleep in here. And let's run this in the background. And if we do our ps-fl, sure enough, there's two copies of F1. And this first one has a parent ID of 25869, that's bash. So this first F1 that's listed was run by typing F1. But the second F1 has a parent ID of 29009. That's the ID of this process F1. So the second F1 was created by the first. All right. So we have a process creation taking place, and those will time out after 60 seconds. But let's go ahead and change this. So instead of printing the process ID, let's do this. All right, so if f-return is not equal to 0, then I'm going to print a message saying I'm the parent, and I'm going to show what the child ID is. Otherwise, I'm going to say I'm the child. All right, so those previous ones have gone away. Let's compile that. I knew I'd mess up my braces somewhere. All right. So we're ready to call fork, and one process reported that it was the parent, and the child's ID was this, and the other process reported that it was the child. So these processes can determine their own identity by looking at that return value from the call. And the thing that's a little weird to think about is that, you know, the cloning happens inside this function call, and after that there are two processes that are assigning a value to fret based on the return from fork, and then going ahead and executing the rest of this code. All right, this is a kind of creepy thing. All right, so I'm going to show you something you do not want to do. Okay, don't do this. This is called a fork bomb. Okay, this will shut down a Linux system. It may not work on the Linux server, but let's not find out. Okay, I put some process limits on student accounts in case something goes wrong, but those limits are pretty generous, and if people do this, there's a good chance it'll crash the Linux server, and that'll bum out people who are in the middle of homework 8. All right, I'm just going to do this thing that we just did inside a for loop, and I'm going to do it 4 times. Okay, now if I did this 100 times, my machine would crash. All right, but I'm just going to do this 4 times. So I'm going to call fork a total of 4 times, but what's going to happen is I'm going to forget a semicolon and save the universe. All right, what's going to happen is a whole lot of action, right? Way more than 4 things. So first there was a call to fork, there was a parent, and there was a child, right? But as soon as that parent was created, it started the second iteration of its for loop, and so on. And so right now we've got 16 copies of F1 hanging out there. All right, now those will go away, but basically what's happening is we're starting our main process. We call fork, and it creates a second process. Okay, that's one call to fork. And now we go back, we do some prints, we go back to the top of that for loop. Both of these go back to the top of their for loop, and they execute another call to fork. And so this main process creates a new process, but so does this copy. So there's our second call to fork. And then when we go back up to the top of the loop, each of these 4 threads makes another call to fork. And then when we go back up to the top of the loop a 4th time, each of these threads is going to make a copy. And so with 4 calls to fork, you get 16 processes. So a fork bomb is just, you know, while one fork. It's a 1-line C program. And if you don't have limits on how many processes a user can create, that basically consumes all the resources on the machine, potentially to the point where the system cannot do things it needs to do. Because, you know, each process, the information for that process has to be saved somewhere. It's saved in something called a process slot. There's only a certain number of process slots. And if those become totally consumed, then any job that wants to create a new process is going to fail. Fork's going to return an error. And if that's a system process that's trying to create something, then the system will likely crash. Definitely don't loop it 1,000 times. I think if you loop it, 30 times, I think if you loop it 20 times, you'll probably crash the machine. All right, but we're being kind and gentle because this is my own machine. So I only did it 4 times, and I had it exit after 60 seconds. So that's good. All right, so that's the basic structure of fork, and that's basically how processes are created. I definitely recommend testing this on your laptop. I mean, it is fun. Especially if you're in a virtual box. Who cares if you crash your virtual box, as long as you don't have critical stuff on it. The machine will hang up and it'll freak out, and maybe it'll panic and reboot itself, or maybe it'll just get really unresponsive. But it's fun to explore, test the boundaries of the system, and so on and so forth. That's what's so cool about doing computer science right now is, you can have your own system and you can virtualize and so on and so forth. All right. So that's the underlying essence of process creation. But we don't always want to go down to that level. That's a pretty fine-grained approach. And it leaves us with an exact clone of our process, which means if we want to do something different, we have to do something after we fork to run some other process or something like that. Let me show you a different version of process creation. So there's another function called system. If we call the system function, we can put in a string which corresponds to a Unix command. And system will basically execute this command and send any output produced to standard out. So if I run this, it says hello, the date is, and there's the date and time. I don't know if I can get away with this. All right, so let's throw this in the background and let's do our PS. And there's some interesting stuff here. So here's our program F2, which is running. Its ID is 652. 652 created this sh-c date semicolon sleep 60, right? So it used the shell called sh to run this date command and the sleep, and then that shell 653 created another process to run the sleep command. So someone asked, where would you use this? Anytime you want to create a process. So when the system boots, right, this is where the processes come from. They're clones of an initial process. When a user wants to log in, you talk to a SSH server to help authenticate your credentials, and once it decides that you're a valid user, it needs to create a new process to start your bash shell in. Well, that's done using fork or something, wrapped around fork. So this is really where all this stuff comes from. Now, as a user, if we're writing C code or we're making a web browser or something like that, we're not going to call fork directly. But things that we are doing will end up calling fork for us. And an example is this system call. If we want to run a Unix command, inside this function, there's a call to fork that's creating a new process. All right, so we are out of time, but we'll pick up from that on Monday and dig deeper into processes. All right. Have a great afternoon. I will see you next time. Thanks.